Uh, Good evening, everyone. Myself Binanda Milli, along with my teammate Rajtilak Chamlagain. Today, I am going to present on our topic called neural network-based learning. Uh, so, first of all, what is a neural network? What is a neural network? A neural network is a machine learning model inspired by the human brain. Just like our brain has neurons that process information, a neural network has artificial neurons that process data and learn patterns. It learns by looking at examples and gradually improving its prediction by reducing mistakes. Neural networks are used in many areas such as healthcare, finance, speech recognition, computer vision, NLP, robotics, etc. So, moving to the next part, uh, artificial neuron model. Artificial neuron model. Uh, this slide shows the basic unit of a neural network called an artificial neuron. Here, x1, x2, x3, and x4 are the inputs. Each input has a weight. These weights decide how important an input is. We also add a bias term, which helps the neuron make better decision. The neuron multiplies each input with its weight and add them together along with the bias and produces a value z. This value then passes through an activation function shows as fz, which generates the final output. Uh, this is the equation where wi are weights, xi are inputs, and b is bias. Now moving to the next part. Loss function and optimization. After making a prediction, the network needs to know how accurate it is. For this, we use loss function. Loss function measures the difference between the predicted value and the actual value. The smaller the loss, the better the model performs. For regression problems, we often use mean square error or MSE. For classification problems, we use cross entropy loss. The goal of this training is to reduce this loss as much as possible. Now moving to the next slide called gradient descent. This is the equation. Now here the question is how do we reduce the loss? The answer is gradient descent. It is an optimization algorithm that updates the weights to minimize the loss. The formula is given here where it is the current weight and it is the learning rate or step size, and this is the gradient loss with respect to weight. Now we moving to the next part that is called perceptron learning. What is this? The perceptron is the simplest form of a neural network. It takes inputs, calculates a weight sum, applies a step activation function, and produces an output. And its learning rule is given here. This is the learning rule. This means weights are updated whenever the prediction is wrong. Advantages of perceptron learning are that it is simple and computationally efficient. However, it cannot solve complex nonlinear problems such as XOR. Now we moving to the next part called delta learning rule. The delta rule improves the perceptron learning process. This rule improves the perceptron learning process. First, it calculates the error by subtracting the predicted output from the actual output. Then it updates the weight according to that error. The larger the error, the larger the weight adjustment. This rule is important because it forms the basis of gradient descent and backpropagation. Now moving to the next part called multi-layer perceptrons or MLP. To solve more complex problems, we use this method. It contains an input layer, one or more hidden layers, and output layers. The hidden layers help the network learn complex features from data. Then data moves from left to right during the forward pass. During turning errors move backward through the network using propagation. Now next slide is called activation function. Now what is activation function and what it does? Activation functions mainly helps neural networks learn complex patterns. The three common activation functions are sigmoid. It gives output between 0 and 1 and is often used for probabilities. Then turn, it gives output between -1 and 1 and performs better than sigmoid in many cases. And the last one is relu. It outputs 0 for negative values and the value itself for positive values, and it is the most widely used activation function because it is very simple and fast. Now the next slide is backpropagation algorithm. This slide explains how neural network actually learned. In step 1, the forward pass, the network generates predictions, and the second is loss calculation, where the prediction error is calculated, and in third backward pass, the error is propagated backward through the network using chain rule, and at the last weight update, the weights are adjusted using gradient descent. This process repeat many times until the model achieves good accuracy. Now the next part will be explained by my teammate Rajtilak Chamlagain. Thank you.
So is Binanda just established the foundation mechanics of how neural networks learn and processes data are incredibly powerful. I will be taking over for the second half of our presentation to discuss how we actually apply this architecture to specific tasks, how we optimize them, and where they are used in the real world. Let's begin on slide 11 by looking how multi-layer perceptrons handle classification tasks. We generally categorize this into two domains. Let us see. So one is binary classification, the other is multi-class classification. Moving into practical application, let's discuss how multi-layer perceptrons handle classifications. We generally categorize this into two domains. First, binary classifications, where the network makes either or decision like identifying spams or diagnosing a disease. Here we typically use a single output neuron with a sigmoid activation to get a probability. On the other hand, multi-class classification addresses more complex scenarios like recognizing handwriting digits or sentiment analysis. In this case, we use a softmax activation layer across multiple neurons, ensuring the total probability sum to 1. The choice of loss function is critical here. Binary cross entroms for two classes and categorical cross entroms for entropy for multiple classes. So moving to slide number 12. So now we will see the predicting continuous values. While classification deals with categories, regression is about predicting continuous real valued number. Think of house price predicting of weather forecasting. Architecturally, the key difference lies in the output layer. We use a linear activation or sometimes no activation at all, allowing the output to be unbounded. During training, we rely heavily on mean squared error or MSE. This function is particularly effective because it squares the difference between predicted and actual values, penalizing the large errors much more severely. This ensures our model fits the general trend of the data without being swayed by minor fluctuations. So next, about regularization techniques, a major challenge in neural network is overfitting. So where the model essentially memorizes the training data but fails to generalize the new information. To combat this, we use regularization. L1 and L2 regularization added a penalty, as we can see, to the loss function based on the size of the weight, preventing any single neuron from being too dominant. Dropout in another powerful tool by randomly deactivating neurons during training. We force the network to learn redundant representation, making it more robust and preventing it from relying on specific internal crutches. So next we will see the early stopping. So building on regularization, early stopping is highly effective strategy to optimize training duration. As you can see in the trend chart, that while training loss consistently goes down, the validation loss eventually started to rise. The inflection point is exactly where the model stop learning patterns and start memorizing noise. By monitoring the gap, we can stop the training automatically at the peak of the generalization. This not only prevent outfitting but also saves significant computation resources and time. So next we will see the introduction to deep learning. So deep learning is some other concept. Now let's look at it in it. Deep learning is essentially an evolution of traditional machine learning. The fundamental shift here is for manual feature engineering to automatic feature extraction. In traditional machine learning, experts had to define which data features were important. Deep learning, through its many hidden layers, identifies this feature itself. At the data volume increase, deep learning model continues to improve in performance, whereas shallow models tends to uh, plateau. It is the scalability that has fueled modern breakthrough in speeches and visions. So next we will see about the recurrent neural network. So when dealing with sequential data like text, speech or time series, standard networks fall short because they have no memory. This is where recurrent neural network or RNN come in. By feeding the output of one step back into the next, RNNs maintain a hidden state that acts as a memory. However, standard RNN often struggle with long sequential due to the vanishing gradient problem. To solve this, we use specialized units like LSTMs and GRUs, which use gates to decide exactly what information to remember and what to forget over long time. So next we will see convolutional neural network. So for visual data, convolutional neural network are the industry standard. Instead of processing every pixel independently, CNN use filter to detect local patterns like edges and texture through the convolutional layers. As you can see, this preserve the spatial structure of the image. We then use pooling layers to reduce the dimension and computational load, focusing only on the most important feature. Finally, the full connected layer at the end use this extracted features to classify the image. This architecture is the backbone of everything from facial recognition to autonomous driving. Next, the model comparison. To summarize our architectural option, if you are dealing with simple linear separatable data, a perceptor is sufficient. For standard tabular data, a multi-layer perceptor is your go-to. If your data is an image, a CNN is non-negotiable for spatial feature excretion, and for anything involve a sequence or time, and RNN or LSTM is required. Choosing the right architecture is often the most important decision in the entire pipeline, as it determines the model's fundamental capacity to learn from your specific data type. So next we will see the applications of neural networks. So the impact of the network is visible across every major industry. In healthcare, we are seeing drug discoveries, timelines, slashes, and diagnosed accuracy improved through medical images. In finance, algorithmic trading and real-time frauds detected rely on the speed of the neural network. Even in the automotive sector, autonomous vehicles use a fusion of CNN for vision and RNN for path planning. We aren't just building models, we are building the infrastructure for a more automated and effective world. So the conclusion, in conclusion, we have explored how neural network model complex pattern by mimicking biological system. We have seen how back propagation allows this model to learn, and how techniques like regularization and early stopping keep them reliable. Whether it's through the spatial awareness of CNN or the temporal memory of RNN, deep learning has moved beyond a theoretical concept into a transformative technique. The journey from a simple perceptrons to a large language model represent one of the great leaps in computational history. So thank you for your time today.